So for today's colloquium, we welcome Andrew Yarmola from the University of Luxembourg, but he's at Princeton University right now, who's going to tell us about circle packings and Delaunay circle patterns for complex projective structures.
Thank you so much for having me. It is a pleasure to be here. As always, pleasure to see Reese and to meet everybody else. So today I want to talk about circle packings and the sort of a wider generalization of Delaunay circle packings on this thing called complex projective structures. So let me try to kind of give a background a little bit on circle packings. So for most of the talk, except for specific cases, we're going to talk about a surface S of genus least equal to 2. So if you're not familiar, what I'm talking about is a surface that looks like this. And if you give the surface a metric, in particular, let's say hyperbolic metric, you can define circles on it. And a circle packing is a finite collection of circles such that the complementary regions are ideal hyperbolic polygons. So let me maybe remind you what hyperbolic geometry is, or at least hyperbolic metric. So the universal cover of this is a simply connected disk. And one way you can think about it is the space H2, which is sitting inside of the complex numbers, which is just all the numbers where the imaginary part is z, such that the imaginary part of z is bigger than 0. And then the metric on it is going to be dz over the imaginary part of z. And this is a complete Riemannian metric where the geodesics, the complete geodesics looks like this. So they look like little guys like this. So this here is the real line, and the complete geodesics starting at a point look like semicircles that are perpendicular to the boundary or straight lines that are perpendicular to the boundary. And then the isometry group, the orientation preserving isometry groups of H2 can be identified with PSL to R. I apologize if this is hard to read. Let me switch to a different chalk, maybe it'll be a little easier. Where the action is Z, so a matrix, let's write it as A, B, C, D, acts on Z by what are called Mobius transformations. Right? So this is the Mobius transformation action. This is called Mobius action. Right? So, and in general, you can think of Mobius action as PSL to C acting on CP1. Okay, using the same exact formula. Right, so here we have the real numbers that preserve the upper half space, they act by this. And now this metric, how do we give it to a surface? Well, we just need a way of representing its fundamental group inside of here, right? So if you have gamma that is isomorphic to pi 1 of s, that sits inside of, let's say, let's do it this way, pi 1 of s isomorphic to gamma, sitting inside of PSL to R, the quotient gives us H2 mod gamma, gives us a hyperbolic structure on S. Right? And now we can define circles as just, or disks as all the points that are distance r, at least at most r from a point. And what do I mean here by the last thing, this Mobius equivalent to an ideal hyperbolic polygon? Well, Mobius equivalent means that under the action of PSL2C, as a piece of CP1, we can get it to what is an ideal hyperbolic polygon. It is something that looks like this. Or actually, maybe let's not include the point of infinity, let's just draw it like this. Right, so this is an ideal hyperbolic polygon. It is the convex hull of these points at infinity. And these are all little geodesics. So this is an ideal polygon. And if you know the action of the Mobius group, you can actually conjugate this to a circle so that it looks like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Is this equivalent to saying that the circles are tangential, or?
So circles are, yeah, this is equivalent to the fact that the circles are tangential, but it's more so. This isn't just some quadrilateral. This quadrilateral lies on the opponents, and this quadrilateral lies on the boundary of the circle. That's an extra condition. So in particular, you can actually define things called dual disks, right? So there's this complementary regions give us these dual disks. Right. Any other questions? Okay. And so what you can do with this is you can actually define a polygonal cell decomposition associated to your disks. So what you do is you put a point inside of each circle, and for every point of tangency, you draw a little line. So now your surface is decomposed into, you get a vertex for every circle that you had, or disk, and then you have an edge for every tangency point, and then you have a face for every complementary region. And it's polygonal, in particularly in that this, that there are actually edges to this polygon, and there's no two gons, and everything when you lift it to the universal cover, the one skeleton is simple. So there's no like loops in the lift to the universal cover. So you really are kind of gluing polygons in some regions. So one remarkable thing about this is you might ask, okay, so if you have one of these, can you go backwards? So when can you recognize a polygonal cell decomposition as a circle packing? And the Kolbe-Andreev-Thurston theorem, first proved by Kolbe for spheres, and then Andreev and Thurston in a more general case, says that there actually is a way to do it, and it's sort of unique. So if you want to take a cell decomposition and realize it as the nerve of a circle packing, there's only one way to do this in a hyperbolic setting. So that is a very kind of strong, remarkable theorem. And here this holds for all closed surfaces, including the sphere and the torus as well. Now the next thing you might ask, what do surfaces that admit a circle packing look like? So if you're familiar with Teichmüller theory, you know that the space of hyperbolic structures on a surface is 6G minus 6 dimensional, is a deformation space called the Teichmüller space. But the problem is, if you just take combinatorial objects, cell decompositions, you're only getting a countable set. So this countable set gives you a point in Teichmüller space. So the space of hyperbolic structures is called Teichmüller space. Right? And so this is homomorphic to R to the 6G minus 6, where G is the genus of the surface. And here I'm talking about Mark structures, so think about taking all gammas that are isomorphic to pi 1 up to conjugation by PSL to R. Think of that space. And here we only have a countable set, so one cool thing is a theorem of Brooks that says the structures that admit a circle packing are actually dense in Teichmüller space. So it's kind of a neat little fact.
Can I just ask a question about what this theorem means? The first thing.
Mm-hmm.
So a polygonal cell decomposition, S doesn't have a metric on it.
Yes.
So this is just a bunch of points with a bunch of continuous curves?
Yeah.
That's it?
Yeah.
Just points and curves.
I mean, this is up to isotopy. So here, sorry, this equality should be an isotopy.
So, and two polygonal cell decompositions are considered the same if you can vary one of the, if they're isotopic?
Yes.
Okay. I see. So given one of these very, very floppy, without much structure, you're saying that there's a unique structure so that you get a picture like that.
Mm-hmm. Locally, I mean, I don't have a, it's really hard to draw a full picture of a hyperbolic surface.
And those straight lines that you drew, are those hyperbolic geodesics?
No.
Just straight?
Yeah, they're just, those are not actually hyperbolic centers either. It's just, this is just combinatorial for the picture. The circles are actually circles, but the lines are not.
Okay.
Yeah. Yes, you could probably do it.
So the theorem of Brooks
Mhm.
is saying that if you take all the polygonal decompositions,
Yeah.
then you get a test.
Exactly. So that's sort of a, I wanted to put the word Teichmüller space in the first slide. It's a cool thing. So let me maybe give you a motivation of why the covariant theorem is actually cool. So this is a common example, wonderful application. So take some blob in the plane. And now imagine you have hexagonal packing of the plane, and you just look at the circles that fit inside of it. Right? So you have this blob, and these are all, you have this infinite hexagonal packing. I just take the ones that fit inside of my region. And I made it a certain size. I could make it a smaller hexagonal packing. And now I start trying to build the nerve. Right? And so in theory, this right here is almost a nerve of circle packing, except on the outside here, notice I have 9 edges, but they need to be associated to a particular other vertex, right? I mean, I guess you could also have the other face be one of the 9s, but the clever thing that Thurston came up with was add another vertex at infinity and build something like this. So just connect, orange did not work very well, but okay. Connect every one of these outer vertices to a final vertex, and what this final vertex you will want, it will become a disk that will be sort of on the outside when you solve for this. So let me see if I can, for the next slide, no, yeah. So imagine just this commutatorial object, forget the disks. This commutatorial object is a cell decomposition of the sphere of CP1. And now there is a unique, not hyperbolic structure in this case, it's going to be a unique complex structure, but that realizes this with actual round disks. And the picture will look like this, where that vertex that was at the top is the outside disk in CP1, and all the other guys are the ones that appear. So you can actually see the tangency pattern. Here was, I made a triangle. Here's 1, 2, 3, 4, 1, 2, 3, 1, 2, and 1 at the end. And the cool thing about this is it somehow tells you that if you wanted to map this region to a disk, you sort of know what to do with each one of these disks. You know how to get them to where they might want to go. And in fact, it's a theorem of many people that if you keep making this finer and finer, if you take a finer hexagonal decomposition, this construction lets you actually converge to a Riemann mapping from your original region to the unit disk. So it is somehow the power of the covariant theorem to do this. It's sort of a neat thing. But here it's being applied to just the Riemann sphere. No hyperbolic geometry involved. And so that should give you a hint, though, that we have the notion of disks on the Riemann sphere. We don't actually need the hyperbolic metric. So this is where complex projective structures come in. So we can talk about disks without a metric. So let's talk about disks on structures on surfaces as in the most lax sense possible. And to make it as lax as possible, we define a complex projective structure. And to do that, we just think of a maximal atlas of charts to CP1, to the Riemann sphere, and the transition function between every atlas, every chart, is going to have to be a Mobius transformation. It has to be one of these guys from PSL to C acting in this way. Right? And so, and maybe give you a picture of an example. Let me see. Let's start with this first. So, the CP1 structure, right, gives you really a map from the universal cover of S to CP1. And you do this just by gluing up all the charts according to your Mobius transformations, right? You fix the starting chart, and then you start just developing everything out. And though this gives you what's called the developing map of sigma, right? And then you also have the action of the fundamental group up here, right? Pi1 acts here on S tilde, and that gives you a corresponding action by Mobius transformations here. So you get the action of the holonomy of sigma, this is hol of pi 1 of S, is acting here by, as a subgroup of Mobius transformations. So we'll write PSL to C. Right? So what does one of these things look like? So this is a developing image of a universal cover. So this is the image of a developing map of S tilde in CP1 of such a structure. So the yellow part is the image here, and it's injective. It doesn't always have to be. The developing map could wrap around the sphere many times, and it could look terrible. This is an example of what's called a quasi-Fuchsian group. But now, we can define circles in CP1. In CP1, circles are just the circles we're used to. Because, if you know something about Mobius transformations, they send circles to circles. Right? This is one of they're in fact conformal. So we can actually define a round disk in a complex projective structure sigma to be a connected closed subset of the universal cover such that its image under the developing map is a disk and the developing map is injective on it so that there's no weirdness. So something like this, right? So that's the image of the round disk D, and it's just a disk in the universal cover. And if you pull it back here, you'll get a closed subset. So that's what we call disks, right? And you can also talk about embedded disks. So they'll be embedded if, under the projection from the universal cover down to S, the disk goes in without overlapping itself, right? So now you can ask, okay, we have a notion of circles. We have a notion of angles because Mobius transformations are conformal, so we can say, oh, we can have tangency between two circles, right? And we know about embedded disks, so if we look at a finite collection of embedded disks on complex projective structures that are all tangent with nice complementary regions, we can extend the notion of circle packing from hyperbolic metrics to complex projective structures. And so we can ask, what do those things look like? And so, in a series of papers, Kojima, Mizushima, and Tan made a little conjecture. So they built this space. They fix a polygonal cell decomposition, and then they look at all pairs of a complex projective structure and a circle packing. So again, P is an embedded circle packing on sigma, which means that it is exactly, it's exactly the same thing as a circle packing on the original surface, where we look at embedded round disks in S, and we have to make sure that the complementary regions are all of these, are Mobius equivalent to ideal polygons. And they said, okay, what does this space look like? And so they conjectured that it actually should look like Teichmüller space. So what is this map that I'm talking about? What is the forgetful map? So let me erase this bit right here. Since we're not dealing with metrics anymore. So we have the space curly C of tau, right? This is the space of pairs, sigma and circle packing. Sigma is an element of this, and P is a circle packing. And one thing we can do is we can just take this and forget this part. Just look at the complex projective structures, right? So we can consider this map, projection onto the first factor, right? Oh, yeah, let's not give it a name. And then we can take this and go down to Teichmüller space. So how does this work? Well, it works by uniformization. A complex projective structure is automatically a complex structure on a surface. So a complex structure on a surface gives a complex structure to its universal cover. And a simply connected complex one-dimensional complex manifold can either be the complex plane, the disk, or the Riemann sphere. And for surfaces, they end up being the unit disk, which then we can put a hyperbolic metric on, and we go down to Teichmüller space. So there is a forgetful map here that goes down to the complex structure, or hyperbolic metric, on the surface below. And so this map right here is what we call F tau. Okay. And the idea is that this map should be a homeomorphism. So why would that make any sense?
What do C again? Complex structures?
C is the space of all complex projective structures on the surface S. So for brevity, I dropped D, but if this helps. Yeah. So this is Teichmüller space of S. This is the space of complex projective structures on S. And this is the space of complex projective structures admitting a circle packing. So this is the set of pairs that it's particularly important.
So how does this relate to Brooks' theorem? It says that, I mean, I thought there was only a discrete set of things that had circle packings. Now it looks
Hyperbolic
like,
ones.
now it looks like they all do.
Yeah, it's no longer discrete. You don't have uniqueness.
What's not discrete?
So this thing is no longer going to be just, so in the setting of, so let's make one, for example, if S is the sphere, this is first point. So if S is the sphere, this is Kobe's original theorem. When S is the sphere, this is a point, this is a point, and this is a point. So it's not very exciting. But it is a profound fact. This is the thing I showed you. But what happens in the hyperbolic case is that there is, so in the picture, so there's a way to picture, let me maybe make a picture like this. There's a way to picture this space as a product of Teichmüller space and a space called measure laminations. We'll maybe not talk about that, but let's see. So if we try to draw this as a Cartesian plane, where this is the Teichmüller space, and then this is the measure lamination space, the idea is that this is 0 somehow. This is 0 in the measure lamination space. Somehow that this point right here is the Kobe-Andreev-Thurston solution. And this here is the sort of, let's give this a name, pi1 of C of tau. So there's a unique hyperbolic point, but the actual complex projective guys are not unique at all. So there's actually only one point where the circle packing is realized by a structure here that's already hyperbolic. Otherwise, you have to go down by looking at the underlying complex structure. You don't have the hyperbolic metric. That kind of makes sense? So like yeah, so yes.
So this map F tau doesn't come from the uniformization theorem?
No, not in, no, well, this portion does, yes.
Yeah.
Yeah,
So
but here there's a problem. We don't know if this guy is injective. We don't know what this, if this is an embedding or what this looks like. So in general, we consider this space before we really get to understand this space.
I have a technical question. So in the previous slide,
Mhm.
your definition of embedded disk,
Yes.
everything happened in the universal cover.
Mhm.
So I don't know if that's intentional, but you don't want your disks to overlap.
I do later.
But like not, maybe just the boundary, but not.
Self-interrupt later. No, I do want them overlapping later, possibly. But
Oh.
not right now. I mean, so this here, these are embedded circles. For now, we're talking about embedded circle packing. So each disk is embedded and they're just tangent to each other.
Okay.
No overlap, nothing. This is kind of the same picture as before. So this is a list of things that are known. When S is a sphere, I said all these things are points. So it's true. Mizushima proved the conjecture when S is a torus and tau has one vertex, using just computational techniques. He actually showed explicitly what this was. Another thing that can be shown, if tau has one vertex, then Koji and Mizushima have shown that CT is a smooth variety of the correct dimension. Actually, I should really just say they've shown that it's a ball. They have shown that it's a ball of dimension 6g minus 6, and they've also shown that f tau is proper for all genus.
Can I ask something?
Yes.
In terms of this new notion of circles that's coming from the projective complex structures, how can you tell if you're at the point where they're actually hyperbolic?
The image of the developing map will be a round circle. So if you've ever seen like a deformation of a Fuchsian structure, like a quasi-Fuchsian structure, if you look at the image of the developing map, so this would be like dev sigma of S tilde. If it's a round circle, you're hyperbolic. And then it starts getting a little crazy and it looks like that squiggly thing that I showed you. Like that.
So
You can deform into
there's
this.
a unique point where the image of the developing map is a round circle, and that's where
Yeah.
hyperbolic.
Yeah, so this is this cap point. Yeah. There's always going to be one of these. In terms of the actual cap point, so for all tau, you can actually show that there's a neighborhood U right here, such that the map, such that f tau restricted to U is a local homeomorphism. So, well, it's inside of this space, to be more precise, but you can actually say that near here, everything is good. Everything is a local, things are local homomorphism near the Cobian drift, there's a solution. So that's actually a very beautiful argument. And then recently a grad student, graduated student of David Dumas, she showed that f tau is proper for classes of combinatorially interesting cell decompositions. And so what Jean-Marc and I did was extend this properness to all cell decompositions. So this is sort of one step towards the conjecture in total. So the things that we don't have currently are sort of the following. We don't have that C tau is always a manifold. We know that it's a variety, we just don't know it's smooth. We don't have that it's locally injective. I mean, we don't even know if this is injective. And we also don't know if it's connected. So there's approaches to all of this, but it's still an open question. Let's see. Maybe let's see, what's the next slide? Yeah. So before I go to the line circle package, any questions? Let me maybe show you what I mean by all of this. So let me see if I can give you, I'll get out of full screen mode. So let me show you what circle packings kind of look like. So before we start on this project, I wanted to have an idea of what a circle packing with more than one vertex looks like. So this is a circle packing of a torus with two disks. And this is the universal cover of a torus is just C. So I have this tessellation by circles of C. And the blue circle is one circle and the pink circle is the other circle. And this here is a parameter space. And this parameter space represents actually all possible structures that are circle packable. And here I have the output of their traces, the holonomics, and the uniformization. And I can actually write down for you numerically the function that takes from our parameters to Teichmüller space. So let me show you what this looks like. You can actually take this point and wiggle it around, and you can see the structures deforming. So this is like, so the developing image of a complex projective structure on a torus. So this is on a torus now, again, genus 2, we lied. It's going to have two commuting elements that they're called hyperbolic elements. They have the trace of this matrix that I erased, the PSL2C matrix is greater than, let's say, well, the trace is not on the line, on the real line between -2 and 2. And so these would be the fixed points of those two commuting elements, and then the whole map kind of wraps around these guys. So you can actually see them in like this, in this view, you can see sort of this wrapping action. These guys keep wrapping around. And so you can get some pretty nice looking patterns, and as you move around in the space, when you go to the boundary, you sort of get to deformative actions. And right now I'm moving along the imaginary axis in Teichmüller space, so these are all the rectangular, these are all uniformizations that have tori that have rectangular fundamental domains. So this is things like this. Let me show you just one pretty one that I like. This one and 0.645. Oops, no, that didn't get set. Let's go with XC. Yeah, so this is a pretty one. So here what happens is one of the circles is on the outside and it sort of folds, one of the circles comes in and it folds over itself, and you get this infinite, you get an infinite packing of a unit disk. So you get some pretty ones like this. I don't know if these are any, it's kind of hard to hit the right points, but things like this are pretty common. And this is the whole deformation space of these, of complex projective structures that admit a circle packing of this combinatorics. And as you can see, it's two-dimensional, and you have to trust me that it actually maps to Teichmüller space. So yeah, this black line is the ones that lie in the imaginary axis in Teichmüller space, and these are the ones where all the lattices have the lengths of the vectors are the same. So you have a unit 1 left vector, and you have the other one on the unit circle. So it's numerically, everything looks good for torus and this particular cell, the cell decomposition corresponding to this particular circle package. So let's get back to slides. So the way we actually do this is by working in a slightly more general picture. Instead of dealing with circle patterns, circle packages, we work with what's called Delaunay circle patterns. And to motivate this result, if you know what a Delaunay decomposition is, that will be very helpful. But let me define it for you if you don't. So a Delaunay decomposition of a finite set of points, and in this case it will be on our complex projective structure sigma. It's a realization of a polygonal cell decomposition such that the vertices are the vertices that are the set of points that we start with, and each polygon, and the vertices of each polygon lie on a round disk. So here is a realization of a cell decomposition, and here are the round disks. So as you can see, this triangle, its points lie on a round disk, and in fact this round disk contains no other points of V. This round disk also here contains no round points of V. This disk right here, also no other points of V. So this is, Delaunay decompositions are used in computer science and of interest in other means. So the general trick is every face, the vertices line a circle, and that circle, that disk, doesn't contain any other points of your, any other vertices of your decomposition. And so what is a Delaunay circle pattern? Well, it's exactly the collection of these disks. So it's just these guys. And now you might look at this and you might think, I can go backwards, and indeed you can, and it would also look like these vertices are just the intersection points of the disks, except they're not all of them. The vertices, if you have a collection of disks that sort of cover your entire surface, you want a set of vertices to be non-empty. But you also want to consider only the vertices that don't lie in the interior of any disk. So for example, these two disks intersect right here, but that's not a vertex because it lies in the larger disk. So you can define in general what a Delaunay circle pattern is by looking looking for a collection of disks whose union is the surface, such that the set of intersection points of the boundaries which don't lie in any interior is not empty. It will look kind of like this. And one last thing you sort of want is you also want that you always have this, any two points that follow each other, there's always a disk that cuts them off. So for example, these two disks here between these 2 points, this guy right here is cut off by this other disk. So you always want what's called a cutting disk. But I think it's easier to go from Delaunay decompositions to the circle patterns in the picture.
So when do you draw an edge?
So yes, let's look at the cell decomposition. So you draw an edge, if you want to see when you draw an edge, it's exactly when, so let's look here, you draw an edge exactly when the guys go, if you look at a circle, and you go around in a direction, as long as 2 consecutive guys always get an edge. Right? So around this circle, these 2 consecutive guys get an edge. Around this circle, these 2 consecutive guys get an edge. This guy has 5 vertices on it, and then the consecutive vertices get edges between them. That's how you get the cell decomposition. So actually, let's wait. The nerve of a Delaunay circle packing is a little weird. It's actually the dual of this cell decomposition eta. So it's the dual of this thing right here, and it looks like this. Right? So for every face, you get a vertex. For every edge, you get another edge. And you look at this. So the nerve is this dual. It sort of corresponds to exactly when 2 circles overlap, when they sort of cut each other maximally. And if you want to see how this is connected to circle patterns, you just take a circle packing, add in all the dual disks, and now you have a Delaunay circle pattern, right? Every disk contains no other vertices, and the vertices are just the tangency points, right? And then the nerve, in the Delaunay sense, look like this. It's actually different, but it's still kind of the right notion, so we still call it a nerve. So here again, every time 2 circles kind of cut each other, you get an edge. And you don't get an edge for a tangency point anymore. You only get edges for overlaps. Now, one thing that you need to keep track of if you want to do all this, you also want to know the angles between circles that overlap. And so you can define an angle function. So at the points of intersection, you can measure the angle between the normals, right? And you can define an angle function. So for every edge in the nerve, you can assign an angle. So for example, these 2 guys, this dotted circle and this non-dotted circle, they have a pi/2 intersection angle. In fact, when you get a Delaunay circle pattern from a circle packing, all the angles are pi/2. All right, so that's sort of the picture you should have in your mind. And it's almost the case that if this is constant pi/2, then you actually came from a circle packing. You need a parting condition, right? So there's kind of 2 types of vertices in the graph. There's the ones that come from the dual circles and the ones that don't. That's the only other thing you need.
Here you have two families of this,
Yeah.
in this case, but you also have 2 families for general.
No. Here, just take the union for them. I just kept the dots in here just because
Right.
I didn't want to make another picture. So yeah, this is the dots here are exactly the. So yeah, just imagine taking the union of the dual circles and the original.
Right.
Sorry, dual disks and the original disks.
So from a general Delaunay triangle, Delaunay what pattern?
Delaunay sort of patterns. Yeah.
So, there's no way to define 2 families of disks.
Not always. No, I don't think. I'm not sure, but so I mean. We have a small short lemma that says that if your angle function is constant pi/2 and your nerve is bipartite, then you're fine. But then you actually came from a circle packing. But otherwise, we don't We don't know. So
But
this.
here, so like if you take two circles in the same family, say their angle is 0, right? Their tangent.
There's no angle 0.
There's no angle.
There's no angle 0 because these guys have to overlap.
You're looking at these edges.
It's a
Okay.
different, yeah, it's a new, the edges only appear exactly when you have an overlap. So this is a slightly different construction. So this angle function is nice. It satisfies a few things, which if you know something about polyhedra, you probably find familiar. So if you go around the face of the dual packing, you always have to get angle 2 pi, which isn't too surprising because that was going around the vertex. Right? So the general picture you should have in mind is we had some circles that, let's say, all met at a point here, right? And then the dual face is this thing. So if I go around the face, I should get the sum of the angles should be 2 pi, right? And then another thing that happens is that if you go around something that doesn't bound the face, then the sum of the angles is actually bigger than 2 pi. So for example, if I had another guy right here, notice we just have 3 circles overlapping here. If I consider the path that goes like this, little house, then that guy has an angle bigger than 2 pi. And we call such pairs admissible. So in general, this is a condition on cell decompositions, polygonal cell decompositions. So you take a polygonal cell decomposition, you take your angle function. If they satisfy the conditions of the limit, we call them admissible. And now you may ask yourself, okay, can we always find, can we always find a Delaunay circle pattern with those properties? So with that angle function and that original cell decomposition. So we could do exactly that.
So eta is what?
Yeah. Eta is the sort of, eta is the graph that connects these vertices. So it's the
It's like a topological combinatorial.
yeah, it's a topological cell decomposition just like before.
Okay.
Right? So eta is the thing that if you look at your Delaunay disk and you go around in the circle, you connect the edges like this, you get your polygon, and you do this in every single disk. So eta is this, right? Right? So it's the graph that was drawn in black earlier. So it's this guy, that's eta. It's not the graph, but cell decomposition, because we're taking tools. So we can define again the space of pairs where we take a complex projective structure, a Delaunay circle packing, and we want that the eta of D be isomorphic to eta, and that the angle functions be equal. Sorry, it's a topic, but yeah. And then the topology, if you're wondering about how the topology gets around to this, you can actually define a bundle of round disks on the space of complex projective structure, and that's where the topology comes from. You take however many disks you have, you take a product, and you look at that as a subspace. And the bundle of round disks is a finite dimensional bundle. So one thing that's known is that Babenko and Springborn, they actually proved that you can do this. There's a unique hyperbolic structure. So this is reminiscent of the Koch-Andreev-Thurston theorem, but this is for Delaunay circle patterns. So in particular, we know that this thing is not empty. We have the same exact point here.
It's really a generalization. Right?
Yeah, it's a generalization, yeah. And so what we prove in general is that if we have an admissible pair, then this forgetful map is proper. So the forgetful map is again the same thing, except here you replace circle packings with Delaunay circle patterns, and then all the other maps are the same. All right. I'm going to get 10 minutes to tell you how we do it. Which is good. It's only like 2 slides. So how do we deal with this? So we work in hyperbolic.
Sorry.
Yeah.
You can define the angle now.
The angle.
So where C eta theta is the space of
Yeah.
CP1 structure and Delaunay circle pattern.
Yes. Yeah. So this is this space of pairs, CP1 structure, and Delaunay circle pattern. But with the angle function theta. So the angles are measured at an intersection of two circles. So if I have two circles that intersect, look at the point of intersection and look at the angle between the normals.
And this is well defined in the CP1 structure.
Yeah, because the Mobius transformations are conformal. Right. So you're fine. Right, and take circles to circles and they're conformal, so it's a well-defined notion to measure angles. So how do we do this? We work in hyperbolic heads. So it's to use hyperbolic 3 dimensions. 3-dimension hyperbolic geometry looks a lot like other hyperbolic geometry. So here, the way you look at it is really maybe complex number plus t. So this would be like C cross R greater than 0, which will be H3. And then the geodesics are, again, a very similar looking picture. The totally geodesic hyperplanes are hemispheres that are perpendicular. And I could write down the metric for you. It's the same. It's the Euclidean distance divided by the height t here, right? And this space 3, this space H3, this thing right here is sort of called the boundary of infinity of H3, and this is actually can be you can identify it with the Riemann sphere. And in fact, what happens is the isometry group, or the Artin-Preserved isometry group of this is PSL2C, acting as Mobius transformations at infinity. So you sort of extend the action by looking at what does it do to the endpoints of geodesics. If you want to know what it does to a point, take a point, take its vector, take a perpendicular vector, and sort of meander around. You can also define it explicitly with quaternions, but this actually is acting in some ways as Mobius transformations at infinity. And so the one thing you can do is assign to every complex projective structure a non-complete hyperbolic structure on the surface across the real number called a hyperbolic end. So let me try to explain what that looks like. What's a hyperbolic end? Let's see. So the heuristic picture for hyperbolic end will be something like this, which will be this at infinity, and then I'm bending it in the right direction. I never remember. I'm bending it in the wrong direction. And then I do like this at infinity. So this is sort of S cross R bigger than 0. And so the picture is somehow you have sigma at one end, and you'll have this bent guy at this other end. But the way you construct it is if you look at, so this is CP1. If you look at the developing image of your universal cover, you can take the convex hull of the complement, and that will look like a little dome structure. So if this is the developing image, you can sort of convex hull it off and it'll look like this. And it's a convex hull because hemispheres look like this, right? Their totally geodesic planes are cut off, are spheres, hemispheres perpendicular to the boundary of infinity. So if you take the convex hull, you get something like this, and then you quotient out by the action of the group as it was acting on the image of the universal cover. And you can do this in general even when the developing mapper is non-injective. And what you get is you get one end, this is generally E sigma. You get one end that's facing infinity, that's the actual original conformal structure, right? Because in some ways, below these spheres, we still have our developing image. And when we quotient, we get our conformal structure back, so that's the complete end. And up here, right here, you have this thing that's bent along some complete geodesics. And when you quotient out, you're going to get geodesics in the surface. So you actually are bent along what's called a lamination on the other end. So you have one end that's conformal, and one end that, when you actually metrically completed, is a hyperbolic surface bent along the measured lamination. So what I'm saying is that this envelope here is hyperbolic in the path metric, and there's a bend along these guys, and this bend is measured by some measure, giving it amount, and by lamination I mean that these guys never intersect, so these are always simple, complete little leaves. So here, this is a particular one where you took a Fuchsian structure and you just took one geodesic and you bent along it. This is a deformation. It's pictured by David Dumas. And so this is the bent guy. So this is bent along mu sigma. Now, you want to ask yourself, if you have a structure that admits a specific type of circle packing, what are the types of bending laminations you get? Because that's one of the pieces of data that you have. And it turns out that the set of all of these is actually compact. So I drew for you this picture earlier with little ML cross Teichmüller space. And what I'm saying is that this thing right here fits into a compact. These are all the mu sigmas. This is compact, so or pre-compact. So closure is compact. So if you fix eta and theta, the actual complex projection structures you get, their bending laminations at the hyperbolic end can't be too wild. They can't bend too much in any direction. Well, I guess not in every direction, but they can't bend too much. So in particular, they're actually pretty compact. So we're in this direction, we're sort of bounded, which kind of helps us deal with trying to prove that this is proper. Right? Remember, of course, properness is proving that the preimage of a compact is compact. So this is one tool in the toolbox, is showing that the measured laminations that appear on these ends are actually in a finite space. So here's actually what I just said. Yeah, so if K is compact, the results on grafting, and this shows so that the set of sigma appearing in the preimage. So if I just look at the sigma appearing here, so look at the sigma right there, then that's pre-compact. But now we have to deal with the other factor. So we can prove that these guys are pre-compact using some notions of grafting and this lemma about measured laminations. Because if we took a compact thing here, we pulled it back, the product is sort of compact. But what about these guys? Can the, in our case now it's D, theta. Can there be a non-compact situation here? What about the actual circle patterns? Okay, they deform in some way that we don't perceive. Can we have circles that kind of collapse to nothing? And the answer is no. And the way we do this is by looking at what's called ideal polyhedra in hyperbolic ends. So let me make this picture a little bigger so I can kind of explain to you what an ideal polyhedron in a hyperbolic end is. Well, let me try first an ideal polyhedron in general. So an ideal polyhedron is something like this. Let's draw this. So think of this as CP1 right here, and the interior is H3. Then an ideal polyhedron in H3 is something that looks like this. And an ideal polyhedron hyperbolic end is something similar. You have, let's say, this was our developing image, and now we have our little points V here and here. It's the convex hull of these points sort of facing outwards. So you look at the stuff that's between the measured lamination sigma down to the convex hull of the points. So essentially, what you do is you take the end for sigma and you cut off the end for sigma minus V. Right? So whatever exactly that means. And that gives you something that looks very much like an ideal polyhedron. And by that I mean is that near a vertex, it looks very much like a multi-sided like a thing that meets in several ways. So here, if you take what's called a horosphere, you get an Euclidean polygon on the face.
So E is for convex end.
Yeah, E is the end, is the corresponding end for the complex projective structure. So if you have a if you take the points away, then this thing lies particularly completely inside of here. So you can just delete the end, and you get this hyperbolic picture. It's actually kind of hard to draw because it's like you took a hyperbolic polygon, but here, like the rest part is bent. So it's like a hyperbolic polygon, but one part of it is kind of completely bent along this bending measured lamination mu. And so, yeah, so
So E of sigma minus V is this.
it's a hyperbolic
Is it like the convex hull of V in H3?
Yeah, kind of. It's the analog of that. It's the sort of convex hull of that in the hyperbolic entity of sigma.
Right.
Yeah. So one thing that happens here is that so there's a ideal polyhedron gives you a cell decomposition of the sphere. It has edges and has vertices. And it turns out that the decomposition that you get this way is exactly the same as A to sub D. And the boundary of this is, again, it carries a hyperbolic metric, but now this time on a punctured surface. And these set of metrics we call the balance metrics. They're actually special. And there is a bijection between balance metrics and polyhedra that we're not going to talk about. But what's really nice about this is we can measure lengths. And so what happens is that there is a constant L0 such that all closed geodesics in this cusp metric, so this hyperbolic metric on the boundary of your ideal polyhedron, which are contractible in S. So they go around like two vertices here. They have to be the length at least L naught. And this tells you that somehow the actual disks in the circle packing, this disk factor has to stay in a compact region. So that's kind of the last ingredient. So this lemma and sort of compactness properties in the bundle of round disks tells us that the whole preimage of a compact set K here, when you pull it back all the way here, has to be compact. The measured lamination lemma told us the sigmas have to lie in a compact thing, and now this lemma tells us the set of disks that we deal with have to lie in a compact thing. And that's
Because they can't be too small. Is that?
Yeah, they can't be too small. So the idea is, what can't happen is your polygonal structure, you can't have a structure that looks like this. You can't have your polygon in your end can't sort of pinch itself off in this way. So this would be your curve of length L0. This can't get too short. So you have your ideal polyhedron, and you can't have curves that are too short that cut off a punctured sphere. So that's what's happening. And that's it. Thank you.
Any questions? Well, I was just wondering when you said, so here's the conjecture of tan Kojima, and you said, well, we're missing, we don't know that it's smooth, we don't know that it's locally injective. What about surjective?
That's the point. That's the reason for doing properness. So if we have local injectivity and properness, we'll have, and because the Teichmüller space is the volume, we'll have, we get that it's a covering map. And so
That's the theorem. That's the theorem.
Hmm?
Is it not a covering map when it's image?
Yeah, but it's a ball. I mean, the properness tells us that it's going to have to be everything. Because otherwise it would be compact. There's going to be non-compactness statement somewhere in there, but yeah. So C-town must not be compact.
I mean, or maybe you have to know they have the same dimension.
They do, they do. It's easy. You can actually show, so you can define a bijection between this space and the space, for example, the balanced metrics I was talking about, and you can see that they have the same dimension. Also, this particular result, this local neighborhood thing right here, which tells you that, at least locally, it's the right dimension. So,
Well, no, I'm missing.
The dimension is correct. So I can prove to you that this, I can make this space into a variety for you, but I cannot prove to you that it's non-singular.
I mean, am I missing something? It seems not true to me. Like a locally injective proper map, say from R2 to R2, is surjective. I don't think that's true. The image is.
Yeah, it needs to be a closed map.
Okay. All right.
This is where.
Oh, okay. Yeah. Any other questions? All right. Let's thank Andrew again.